So in this session we will continue the legacy of our organic named reactions. Okay, we have already completed 14th organic named reactions on our channel, right? You can go and watch. Okay, so today this is the 15th organic named reaction, that is a Brook rearrangement. That is a very important rearrangement reaction. Okay, it seems to be like a very hi-fi reaction, like the name Brook seems to be like a very hi-fi reaction. It's not like that. Okay, fine. So, and now you are seeing on the screen, this is our general overview of this reaction. This is our general scheme of the reaction. Okay, so this is our substrate. You already know that this is our substrate, and this is RLI, is a reagent we have taken here, reagent, and this is our product. So but how the product form, right? The main thing, we have to know the mechanism. Okay, I just don't write all the mechanism step by step very fastly. It's not like that. Okay, I will tell you every mechanism, reason behind every mechanism, why this happen, why not this happen, if this happen, then what can be the consequences. Okay, so in the organic chemistry, the every proper region behind any mechanism, any step, you should have to be very precise and very crystal and clear. Okay, so that's why to just memorize the reaction, like we have taken here this compound, if we take a RLI, and then the compound will form like this. So in this way you will not learn organic chemistry. Okay, you have to go to the root of the organic chemistry, root of the concept, then you can deal with the any variety of a question. Okay, so that's the main important thing. You have to understand the mechanism. So now let's start to this reaction, Brook rearrangement. First of all, this rearrangement have a various types of variety, like 1,2 Brook rearrangement, and 1,3 Brook rearrangement, and 1,4 also, and 1,5 also. These are the varieties of the Brook rearrangement. They are very similar. All the mechanism will be same. Just it's a difference of I will tell you what is the difference between the 1,2 Brook rearrangement and 1,3 and 1,4 and 1,5. Okay, all the mechanism will be same, just slight difference. I will tell you that what is the difference. Okay, so now we have to go through mechanism of this reaction. So now let's start the mechanism of Brook rearrangement. One more thing, you can also observe that here is a OH, and here you will get OSIR3. It means that here is something, here in this reaction something happening here. What happening? So you observe that this Si3 will migrate onto this. It means that here is in this reaction you will find a migration of silyl. Okay, because this is the SiR3, this silyl group will migrate to this one. So you can also observe here it's a OH, and now here it's in the product you will get a OSIR3. It means here something happening, migration type. Okay, so here is a silyl migration happening in this reaction, but I will tell you in much more detail how this happen. Okay, all the mechanism, all the proper explanation. Okay, so now let's start the mechanism of this reaction. Suppose first of all I am starting from the 1,2 Brook rearrangement. 1,2 Brook rearrangement. Okay, rearrangement. right? 1 2 Brook rearrangement. What happened in this? Suppose we have taken the same examples as we have taken in the general scheme. We have here R1, and now we have a OH alcohol group, OH group, and here is a silicon group is attached here, SiR3, and we have here R2, right? And we have taken here RLI, right? Okay, so what happened? So first of all, you have to be knowledge of this region. What does the RLI do, right? What is the work of the RLI? So generally, you also know that RLI generally work as a nucleophile if their generally work as a nucleophile RLI, RMGX, right? RLI, RMGX, and R2CU, Gilman region. These are generally act as a nucleophile when the carbonyl group is present. When the carbonyl group is present, right? It means RLI is work as a nucleophile when the carbonyl functional group is present in the molecule. But here you can see in the substrate there is no any carbonyl group. There is no any carbonyl functional group in this substrate, right? So, but in this case you have here hydrogen attached to oxygen, and this hydrogen is a very acidic proton, right? This hydrogen is a very acidic proton because this hydrogen is attached to this most electronegative atom, oxygen. Okay, so that's why in that case, if the acidic proton is available in the molecule, then the RLI, RMGX, R2CU, then that reagent will work as a base, right? Then if the acidic proton is present in the molecule, then first of all in the organic chemistry acid base reaction will be happen, and that's why here RLI will be work as a base, because in the substrate we have an acidic proton is available. Okay, so here in this case RLI doesn't work as a nucleophile, so it is wrong here in this case. Okay, but in this case we have an acidic proton in this substrate, so that's why RLI work as a base, and the base work is to take a proton to abstract a proton. So now let's move ahead. So what's happened? Let me undo all this so that I can explain you more better. Okay, fine. So now you can see this RLI this is the RLI, this is a plus. This R minus will take proton of this one, and it will get bond will shift on the oxygen as a negative charge, and now you will get something like this. Here is a O minus, and here is a silicon SiR3, and you have here R2, right? Now you are seeing that now in this molecule we have silicon, and we know that in the silicon there is a vacant orbital is present in the silicon. This is silicon, it have a vacant orbital, in the silicon. So that's why this O minus will donate this electron into their silicon vacant orbital. So now you will get something like this. O, here is a Si, here is a R, here is a R, here is a R. Now this bond will get attached and silicon gets a negative charge. Okay, and here is also R2. These are all R3, right? You have got this 3-member ring, such type of molecule, You got? Okay. Now what happened? Because the silicon gets a negative charge, so we will have to make a stable, and this is a 3-member ring, so that's why we have to break the ring. And how it break? It's break in this way. Let me show you. This bond will get break on this carbon as a negative charge, as a carboanion, and you will find something like this: R1, R2, here is a O, and here Si R3, and here, wait, this is a R2, and here you will get a negative charge on this carbon, and that is a carboanion. Okay, and we have a, what happened next? In the next, what happened? Just do the workup. Just do the workup. So after workup, what happened? This negative charge will take the proton H plus, and it will become like this: R1, R2, this is OSiR3, and this is hydrogen, and this is our product of this reaction. This is the product of this reaction. Here is a R2, right? So this is our substrate, and this is our product. You got a final product of this one, right? So first of all, what happened? RLI attack, R minus act as a base. It will take a proton from the acidic proton from the oxygen, and then the O minus will attack on the silicon, vacant or vital, and then the 3-member ring formation happens. And then because this is a 3-member ring, it will have to be break. It will have to be a stable. So how can we break? We break this ring in this way, so that this carbon will get a negative charge, and after negative charge we have done a workup here, and this negative charge will take a proton, and after this you will get a final product, and this is called 1,2 Brook rearrangement. Okay, this is called 1,2 Brook rearrangement. Fine, this is our product. Okay, so now we see, if you see here, in this case the silicon has made up 5 bonds here. Okay, the silicon has made up 5 bonds. One bond here, wait one second, one bond here, second bond here, third bond here, fourth bond here, and this is the 5th bond. So you can say this is the pentacoordinate silicon intermediate. Pentacoordinate silicon intermediate. Silicon intermediate. Okay, this whole molecule is a pentacoordinate silicon intermediate, right? And this is all the mechanism of this reaction of this 1,2 Brook rearrangement. Now I will show you the second example. That example is 1,3 Brook rearrangement. 1,3. Okay. So, and then I will tell you what is the difference between the 1,2 and 1,3. Right. So now let's start. Let me select all this. Okay, fine. Just make a small and keep aside. Okay. Okay, fine. Yes. Now I am talking about 1,3 Brook rearrangement. 1,3 Brook rearrangement. 1,3. This is our previous part. Okay. 1,3 Brook rearrangement. Right. So in this case, suppose we are taking substrate R1. Here is a OLI, right? SiR3 and here is the R2, right? So what happened? Actually you can also take here OH and then take RLi. So R minus will take proton from this oxygen and it will become OLi, right? So that's why I have written directly without the reason. Okay, so let me write here OLi here right now. Yes, this is O minus, this is a plus. So what happened now, because the silicon have a vacant orbital and this O minus will attack on this silicon. Yes, you can see now what is the difference between the 1,2 and 1,3. So the main basic difference is carbon difference. Okay, here is a 2 carbon between this OLi and this SiR3. This carbon, this carbon. This is a 1,3. But in this case of a 1,2, it is only one carbon. The OH and SiR3 are attached from only one carbon. Okay, there is only one carbon, right? But in this case, in the 1,3 Brook rearrangement, we have difference of 2 carbons here, 1 carbon here, 1 carbon here. So 2 carbons between the OLi and SiR3. That's why we call this 1,3 Brook rearrangement. Okay, right? And now we have to think about that, because this is a O minus will attack on this silicon vacant orbital, and then what happened? This become R1. Here is a O, and now here is a silicon, and here R3, and silicon gets a negative charge, and here we have R2, right? Now here 4-member ring will be formation here. 4-member ring will be formed, and after that, to make a stable, we have to break the bond. So after breaking the bond here, at this carbon get a carboanion, and we got a carboanion OSiR3, and we have here R2, and here is a carboanion, right? And this carboanion, just do a workup here, workup, and after this workup, this carboanion, this negative charge will take this proton and it will become like this OSiR3, and we have here R2, and we have here H. This is our final product of the 1,3 Brook rearrangement. Okay, so till now this is the product. Okay, so till now we have discussed 1,2 Brook rearrangement and 1,3 Brook rearrangement. Now we move toward the 1,4 Brook rearrangement. Okay, 1,4. Okay, so let me erase all this. I hope you have understand the very clear difference between the 1,2 and 1,3. Just difference is number of a carbon between the OLi and SiR3. That's all. Okay, so now let's start 1,4 Brook rearrangement. Let me erase all this. So we have, I am taking example R1. Here is a OLi, and here is a SiR3, and we have R2, right? O minus Li plus, right? So because the silicon has a vacant orbital, so that's why this negative charge will donate their electron into silicon vacant orbital, and the silicon gets a negative charge, something like this. O Si R3 silicon negative charge bond formation, and here we have R2. So what happened? Because this is a 5-member ring and the silicon has a negative charge, so we have to make a stable. And how to make a stable? We have to make a stable, and how can we make? So basically we have to break the bond. And how can we break the bond? To break the bond, and this carbon will get a carboanion as a negative charge. So you have something like this, OSiR3, you will get something R2, and here is a negative charge on this carbon, right? And after that same process, do the workup, you will get product R1, wait, R1, you will get here SiR3, right? And here you have R2, and here after the workup this negative charge takes proton, right? And this is our product form. This is a 1,4 Brook rearrangement. This is called 1,4 Brook rearrangement. Okay, so till now we have discussed 1,2 Brook rearrangement, 1,3 Brook rearrangement, and the third one is a 1,4 Brook rearrangement. Okay, now I am taking some more examples. Okay, let's see. That's a very classical example, very standard example. Okay, now let's start. Suppose we have here tertiary butyl Me2, TBU Me2, wait, TBU Me2, silicon, epoxide here, and this is something like this, Cn, and we have pH, right? And we have taken here is the base, 4 equivalent NaHMDS minus 30 degrees Celsius to 15 degrees Celsius. This is our temperature of the condition of the reaction. And then we are taking pH CH2Br, condition of reaction is minus 10 degrees Celsius to 75 degrees Celsius. Sorry, the temperature of this is 10 degrees Celsius, and we got the yield of the product is a 75%. Okay, so how this reaction happen, right? So first of all, you should have to know that what is a NaHMDS. This is the NaHMDS. Okay, this is a NaHMDS, and it will work as a base. It is a base. And how it looks like? This is Na plus, and here is a N minus. You have silicon, trimethylsilane, Me, and here is also Me. Sorry. Here is also silicane, and from silicane 3 Me groups are joined. This whole molecule is a NaHMDS, right? NaHMDS. This is a nitrogen, and this is the ionic bond between this Na plus and nitrogen. Okay, so this is the NaHMDS. If you want to write KHMDS, then just substitute the Na plus from K plus. That is called KHMDS, right? And this is a work as a base, and the work of the base is to take a proton. So what happened next? See, let me erase all of this. Okay, let me select because it takes more time. Okay, fine. Yes. So here we have a hydrogen here, and this hydrogen is a more acidic proton. I hope you all know that that why this hydrogen is a more acidic proton. Okay, because after this proton removal, the negative charge will stabilize by this cyanide ion and the pH group. Okay, so that's why this hydrogen is the most acidic proton in this molecule, right? So what happened? Oh, sorry, wait, yes. So what happened? The base will take proton, this base comes, NaHMDS comes and take proton from this, comes and take this proton, H plus, and now you get something like this, PBu Me2 Si, and here cyanide, and here you have a pH, and here we have negative charge, right? We can also talk about the stereochemistry here, right? So actually this group is below the plane and this group is above the plane. So let me show you. Okay, let me show you. So this is the below the plane, this is the below the plane, and this is the above the plane, right? So this negative charge, and because we have a 3-member epoxide ring, and we know that epoxide ring is a 3-member ring is unstable, so it wants to be break. And how it break? This negative charge will attack on this epoxide, right? And it will break. So after that you got something, PBu Me2 Si, yes, O minus here, and we have something like this. This is our Cn here, and this is pH. Okay, so it will form like this, right? Because we have a 3-member ring, and to break the 3-member ring, so that's why this negative charge will attack on this epoxide, right? And after the attack, what happened? This silicon, let me show you also hydrogen also, because on this carbon we have also hydrogen, right? And here is also a hydrogen. Wait, this hydrogen is above the plane. So let me show you. This is the hydrogen. Okay, so what happened? Because this O minus, and we know that silicon has a vacant orbital, so that's why O minus will attack on the silicon. O minus will attack on the silicon, and then you get something like this. You have here Cn, you have here pH, and you have O minus, right? And here silicon, Me2 TBu, right? And we have something like this, and here we have a hydrogen that is above the plane. Okay, and the silicon gets a negative charge after the oxygen attack on the silicon. So what will happen in this reaction? You already know that after the attack of the oxygen on the silicon gets a negative charge. So we have to make a stable. So we have to make a stable to this compound. So what we'll do? We break the bond. We break the bond like this. Okay, but if you break the bond like this, and this bond is working as a living group, because this bond is working as a living group, because if the silicon bond will get break and it goes on the carbon ion, and that carbon ion shift to this one, this carbon position, and then this bond will be leave. So but we have to do an anti-periplanar elimination. It means the both bond, okay, the both bonds should be anti-periplanar, and then we can do elimination. Okay, so what we have to do, because now we have this bond, we have this bond, so these two bonds are not now these two bonds are not anti-periplanar. Okay, so we have to first make an anti-periplanar, and then we have to do elimination. Okay, so first of all, what we can do, I hope you all understand what is the anti-periplanar. It means something like this, something like this. It means this bond, opposite. It means the anti, this bond in this direction, this bond in this direction. But here in this case, you have this bond in the same direction, this bond is also in the same direction. This is not an anti-periplanar. So we have to first make an anti-periplanar. So how can you make? So you can make, yes, you can make the you can do elimination by anti-periplanar by rotating the single bond. Okay, by rotating the single bond. How can we do? Let me show you. So what happened? Here is a below the plane, right? And you have simple bond. Okay, so you have to rotate the bond. Okay, so after rotating the bond, this oxygen, this whole compound is on the below the plane, right? This is below the plane. So after rotation, this below the plane goes into the above the plane, and this hydrogen will go in the below the plane. Okay, because we are doing bond rotation. So after bond rotation, those bond who are in the below the plane, that bond will come in the above the plane, right? I hope you will all know this bond rotation. Okay, so let me show you what is the formation of the product after the bond rotation and the stereo, because a stereo is more important here. So let me erase, right? Let me erase. Wait. Let me erase here. First of all, sorry. Yes. So after the bond rotation, you will get something like this. This silicon will get above the plane. Okay. So you will get something like this. Silicon here, and here oxygen, and here you have, and that hydrogen, this hydrogen will go below the plane after the bond rotation, right? And now what happened, because silicon has a negative charge, and here Me2, and here is a TBU, and now we keep the same thing, this here Cn, here we have pH, right? So now the anti-periplanar elimination will occur. And how does it occur? Let me show you. Because the silicon gets a negative charge here, okay? Because the silicon gets a negative charge, and to make a more stable, so we have to break the bond. And how can we break the bond? We have to break the bond and add like this one, and then this bond, and this bond. Now this is an anti-periplanar. Okay, so that's why we have to this is the importance of rotation of bond to make an anti-periplanar elimination, right? So that's why when the bond will get break, and then this will bond get break, and then the negative charge will get on this carbon, and this negative charge is stabilized by this by this cyanide withdrawing group and this pH group. Okay, let me show you, let me erase. This question is very fantastic question. Okay, this is a very standard question. So what will happen next? You will get something like this. You will get double bond here. Here is the oxygen, and you have here Si Me2 TBU, and you will get something like this. Here is a Cn, here is a pH, and here is a negative charge, right? And because here is a cyanide we have, so this negative charge is stabilized with the cyanide, because cyanide is applying a minus M effect on this negative charge. So this negative charge will get delocalized and got on the nitrogen as a negative charge. Okay, but we have taken another region also, PHCH2Br, in the second step, PHCH2Br. So what will happen? Let me show you more clear. This negative charge will shift here, and then this C triple bond N, the pi bond of the one pi bond of this C triple bond N will get shift on the nitrogen as a negative charge. Okay, so but here we have, in the second step we have also a reagent here, PHCH2Br. So now we also know that carbon is a more good nucleophile, so that's why the carbon, the attack on this CH2 will be from carbon. Okay, so that's why this nitrogen negative charge will get come back, and then this double bond will get attack on the CH2 and the Br will be leave, right? And then you get the product something like this. Here is a double bond, and here you have Cn pH. Now you have something like this. Here is the O SiMe2 TBU. This is our product. Here the Z alkene will be formed. Z alkene will be formed, and this is our product. Let me underline this so you can see clear. Oh wait. This is our product. Okay. This question is very important question because and we have to also consider here a stereochemistry also. Okay, right? So this question is very a standard question, right? It means in this question all the concepts are mixed. That is a multi-conceptual question. It has a Brook rearrangement also. It has a elimination, anti-periplanar elimination also. You have to be a good knowledge of stereochemistry also, right? Okay. So this is our product, final product of this reaction. Now I am taking something different example. That is our last example of this question. Okay. So now let's see. This is our last example. That is a very good example. That is also very easy also. Okay. That seems to be very hard, but that's a very easy. Okay. If you have understand the concept. Okay. Now let's take last example. Suppose we have S here. Once again. S sulfur, and here is a Me, right? This is sulfur, okay? This is sulfur atom attached to this carbon, right? And from this carbon we have taken here a group something like this, butyl group, and here OH group, right? Okay, fine. And we have taken here reagent KHMDS. I have told you earlier that NaMG, NaHMDS, KHMDS, these are the base. Okay, these are the base. So the work of base is to take a proton. So that's why this base will take proton of this oxygen. This proton, because this proton is a more acidic proton, right? So you will get something like this. Sulfur here, sulfur, and here also this is a Bu group, butyl, and here is a O minus, and you have sulfur here Me, this is Me, and this is Me, right? You can see actually this is also a 1,5. This is a 1,5 Brook rearrangement. Brook rearrangement, right? So what happened? I have told already that because, oh sorry, here is a silicon. Okay, sorry. This is a silicon. Really very sorry. Okay, this is a silicon. Okay, fine. So what happened? This O minus, because sulfur has a vacant orbital, so that's why O minus will donate electron in the sulfur, and so that's why silicon gets a negative charge, and you will get something like this. Silicon, here is a Bu, and here is a oxygen. The bond get attached to oxygen to silicon, and we have 3 Me groups, so I am denoting this Me3, and silicon gets a negative charge. Okay, fine. 1 2 3 1. Oh, okay, one bond gets more, so we have to decrease the bond, right? So something like this. Oh sorry, we have 1 bond, 2 bond, 3 bond, 1 bond, 2 bond, 3 bond. Yes, here is a Bu, right? So 1 bond, 2 bond, 3 bond, and here is a 5-member ring formation here occurring here, because 1 2 3 4 5. Okay, so what happened? We have to break the bond now, right? Because silicon gets a negative charge, so we have to make a more stable. So how can we neutralize the silicon negative charge? So we have to break the bond, and after the breaking the bond, this bond will get break, and it goes on the negative charge on this carbon, and it will become a carboanion. And after the formation of a carboanion, we already know that we have to do a workup, right? We have to do a workup. Here is a sulfur, and you have got a negative charge here, and this is a, okay, wait, because this bond is already broken, so O SiMe3, and here is a Bu. Okay, fine. And now, because do the workup in the last step, do workup here, so this negative charge will take a proton, and it will become like this. Let me show you. After the protonation, after the workup, that negative charge will take a proton and form hydrogen bond here, and this is our final product. This is our final product. Okay, this is our final product, right? Okay, fine. So basically 1 2 okay 1 2 3 4 5 6 bond formation here. Sorry, we have a 6 bond here. I am really sorry. Okay, we have a 6 bond here. 1, 2, 3, 4, 5, 6. Okay, we have a 6 bond forms in the 1,5 Brook rearrangement. You can also predict, right? If you have given a 1,5 Brook rearrangement, then you have to be predict that okay, it's a 1,5. It means that in somewhere the mechanism of this reaction, somewhere a step, the 6 member ring will be formed. It means that 1,5, one more member ring formation happening other than the name. It means this reaction is a 1,5, right? 1,5, but here in this reaction, in the mechanism, we got a 6 member ring, right? So if somewhere written 1,4, it means in that reaction the here it's written 4, but in the reaction you will find 5 member ring formation. Okay, right? Sometime suppose you have written 1, 2 Brook rearrangement. 1, 2 Brook rearrangement. It means that in that mechanism, in that reaction, you will find somewhere in the step you will get a 3 member ring. It means more than one. This is written here. Okay, so you can predict, right? So this reaction is a which type of a rearrangement. Suppose I have given you a question and I ask you, okay, tell me in all these options which are the 1,4 Brook rearrangement. So how can you identify? Okay, so you have to make the mechanism, and after that mechanism, okay, you will get a ring also, because in the step you must get a ring formation. Okay, and count the number of count the how much member of ring you have formed in that reaction. Okay, just subtract 1 and that will be your rearrangement reaction. Okay, so I have taken here example. Here is a 1,5 Brook rearrangement, but in the actual mechanism, if you do the mechanism, then you will find that you got a 6 member ring formation in this reaction. Okay, the name is a 1,5, but you get a 6 member ring formation. The name is a 1,2 Brook rearrangement, but you will get a 3 member ring formation. The name is a 1,4 Brook rearrangement, but you will get 5 member ring formation in that mechanism. Okay, so that's all about the Brook rearrangement. I hope you all understand very clearly, very precise and crystal and clear. And if you have understand very clearly, then please like, share and subscribe the channel of our organic chemistry, because I will teach you only organic. No any other subject. I will teach you only organic. Yeah, okay. So I have also taken a promise to complete the 200 name reactions, very important name reactions on my YouTube channel with a step-by-step full detailed mechanism. Okay, so keep subscribe, like, share and subscribe to this channel for more and more organic chemistry reaction mechanism related video, and I'm pretty sure you will gonna fall in love with organic. Okay, so तब तक के लिए टाटा बाय बाय, सी यू सून इन द नेक्स्ट एपिसोड सीरीज ऑफ अ नेम रिएक्शन. तब तक के लिए बाय बाय. थैंक यू फॉर वॉचिंग माय वीडियो.